We are not guaranteed to make the correct decision by this process of hypothesis testing. Maybe you're beginning to see that there's always some level of uncertainty in statistics. When we conduct a hypothesis test, we choose one of two possible conclusions based upon our data. When the p-value is less than alpha, we reject the null hypothesis, and either you have made the correct decision when the null hypothesis is false, or you've made an error called a type 1 error, and rejected HO when in fact HO is true. In this case, your data happen to be a rare event under the null hypothesis. We do control this probability by our significance level, alpha, and thus in general this will happen no more than 5% of the time using the common significance level of 0.05. When the p-value is greater than alpha, we fail to reject the null hypothesis, and either you've made the correct decision when the null hypothesis is true, or you've made an error called a type 2 error and failed to reject the null when in fact the null is false. This probability is not controlled. How large it is will be determined by the sample size and how much the sampling distributions overlap between the null value and the true value. Here's a visual representation of the 4 possible choices in hypothesis testing. No matter which decision we make, reject the null or fail to reject the null, there is the possibility of making either a correct decision or an error. A type 1 error occurs when we falsely reject a true null hypothesis, and a type 2 error occurs when we fail to reject a false null hypothesis. Be sure to keep these 2 errors straight. This image can help. Both of these probabilities are conditional probabilities. The probability of a type 1 error is the probability that we reject the null hypothesis given the null hypothesis is true. This is easy to calculate as the null distribution will be known. The probability of a type 2 error is the probability that we fail to reject the null hypothesis given the null hypothesis is false. This is impossible to calculate as we do not know the true value if the null hypothesis is false. We can only make guesses at the truth and determine the probability in those cases. Here is a situation where the null hypothesis is that the population mean is 100, and the true value is indeed 100, so the null hypothesis is in fact true. Values in the shaded region would reject the null hypothesis, and values not in the shaded region will fail to reject the null hypothesis. In this case, the data observed did not fall in the shaded region, and thus we fail to reject the null. Since the truth about the population is that the mean is 100, we've made the correct decision. This should happen about 95% of the time when we use an alpha of 0.05. Here again, the null hypothesis is that the population mean mu is 100, and the true value is indeed 100. So the null hypothesis is in fact true. It took a while to find one, but here's a sample where the value falls in the shaded region and we reject the null hypothesis when in fact the null hypothesis is true, which is a type 1 error. This should happen only about 5% of the time if we use an alpha of 0.05. Here is a situation where the null hypothesis is that the population mean mu is 100 and the true value is instead 110. So the null hypothesis is in fact false. In this case, the data observed did fall in the shaded region, and thus we reject the null. Since the truth about the population is that the mean is 110, we've made a correct decision. The chance of this happening varies and is based upon the sample size taken and how far the true value is from the null value, which determines how much overlap there is in the underlying sampling distributions. In this case, it didn't take long to find a value that rejected the null hypothesis. We will define this probability as the power of the test to detect the specified difference, in this case 10 units. Here again, the null hypothesis is that the population mean mu is 100, and the true value is instead 110. So the null hypothesis is in fact false. Here is a sample where the value falls outside of the shaded region, and we failed to reject the null hypothesis when in fact the null hypothesis is false. This is a type 2 error. As in the previous example, the chance of this happening varies and is based upon the sample size taken and how far the true value is from the null value, which determines how much overlap there is in the underlying sampling distributions. In this case, it didn't take long to find a value that failed to reject the null hypothesis. This is because the probability of a type 2 error in this exact situation is 0.374. There's a 37.4% chance of making a type 2 error if the true mean is 110 and the null hypothesis value is 100, using this sample size and our alpha of 0.05. Here is an illustration of the type 2 error probability. On the top, we have the distribution assuming the null value of 100 is true. The blue line represents the cutoff for significance. Values above the blue line will result in rejecting the null hypothesis. On the bottom, we have the distribution using the true value of 110. The blue line continues through. If we want to find the probability of failing to reject the null hypothesis, which would result in a type 2 error, then we need to find the area to the left of the blue line on this bottom distribution. You can hopefully believe from the picture that the shaded area in the bottom picture is 37.4%. You don't need to worry about how to find this value. We simply wanted to help illustrate the idea of the probability of a type 2 error. If we change our alpha level, this does have an inverse relationship with the probability of a type 2 error. Here we have the same situation, but using an alpha level of 0.01. The blue line must move to the right to decrease the chance of a type 1 error, but the result is that there is a much larger chance of making a type 2 error. Now it's 64.4%. What would happen if we reduce the alpha level to 0.10?